Now, the second state of matter for the perfect substances, let us say we say the perfect fluid. The perfect substances which are having non-zero bulk modulus, but having the zero shear modulus, they are termed as perfect fluid. The perfect fluid always can withstand the normal stresses. However, since their shear modulus or rigidity is 0, therefore, they cannot withstand the shear stresses, and that is what we began with our discussion. And we stated earlier also that the fluids, in contrast to solid, cannot withstand the shear stresses, and the shear stresses when applied over the surface of a fluid, then it continuously deforms no matter how small the shear stress is, and it is a time dependent phenomena which is governed by Newton's law of viscosity. Now, the perfect fluid also can be categorized as the perfect liquid as well as the perfect gas. So, now what is a perfect liquid? A perfect liquid says, in terms of if density, if we say, which is given here, is that when we say here, let us say compressibility, in terms of the compressibility rather than seeing from the bulk modulus, if we see here minus 1 by rho d rho by dp. What we say here, the compressibility, when the change in density of a perfect liquid, when this is 0, then the compressibility comes out to be 0. That means a perfect liquid is always incompressible. And in reverse case, since the compressibility is reciprocal of the bulk modulus, the bulk modulus of perfect liquid is almost a very large number, that is infinite. In real cases, the compressibility of a ideal gas, though it is assumed the 0, but in real cases none of the fluids are really incompressible. So, but however, in majority of cases, to assume the flow to be incompressible, their bulk modulus is very high. Now, the second categorization, that is in the perfect fluid, is the perfect gas. From the mechanics, classical mechanics or moduli point of view, we can say that a fluid with 0 rigidity, that is n is equal to 0, but the bulk modulus defined in accordingly to process, that is if the process is carried out isothermal, that is keeping the temperature constant, then kT, which is given as minus V del P by del V, can be written as P using the equation of state for an ideal gas, which is nothing but PV equal to nRT, and for 1 mole PV equal to RT, or we can also essentially denote as P equal to rho RT. Using that expression, if these expression, we can evaluate that kT, that the bulk modulus at isothermal conditions, that is isothermal bulk modulus, comes out to be P. However, when the process is carried out isentropically, then since the isentropic process are governed by the expression PV to the power gamma is equal to constant, from this if you differentiate, then dP by dV can be obtained as gamma P. That means the isentropic bulk modulus is nothing but gamma P. If you take the ratio of Ks and Kt, what essentially you can see that the Ks by Kt, that is the isentropic bulk modulus and isothermal bulk modulus, their ratio is equal to gamma, which is essentially the ratio of Cp by Cv. It means that on a PV diagram, the gamma essentially is the slopes of isentropic and isothermal curves, which we have seen in our school physics days, where we have seen the pressure volume for various processes: isothermal, isentropic, isochoric, adiabatic. In these processes and various thermodynamic cycles, we have seen there on the PV diagram, the isentropic and isothermal curves, basically their slopes are defined by this gamma. We move ahead towards the real conditions. We have discussed so far for everything, all the discussion was based on the ideal gases. Now, kinetic theory of gases not only deals the gases which are in thermodynamic equilibrium, but it also deals, that is, discussion can also be extended for those gases which are not in thermodynamic equilibrium. Moreover, these gases where they are not exactly ideal, but they have the real properties, and these real properties essentially tries to, such as these properties, such as they are called the viscosity, the coefficient of thermal conductivity, and diffusion coefficient. They are called transport properties. That means kinetic theory of gases deals that a gas which is not in thermodynamic equilibrium, it means these properties essentially tries to bring a non-thermodynamic equilibrium system towards the thermodynamic equilibrium. Let us review these properties in brief. The first property is the coefficient of viscosity. Please note that the fluid whenever flows, it flows in the layers, that is lamina we say. That means when the upper layer flows at a higher velocity, then whenever the shear stress, as we see that when the shear stress is applied over the surface, it tries to move the upper surface in the forward direction. That means if this is the layer or fluid medium, if this is the fluid medium and we are applying the stress over here, then it means the upper surface starts moving. However, because of this layer in turn tries to drag in this layer in forward direction, which in turn moves this layer in forward direction. However, because of this process, there exists a velocity gradient in the perpendicular direction, and we know that this velocity gradient can be written as del u by del y if this is x along this axis and this is y axis. That means the fluid layers start moving at different velocities. Because of this, and due to the presence of velocity gradient, the shear stresses are generated between the layers. Moreover, the gases which in the gases which are having the molecules very distant apart and they are free to move from one layer to another layer, they also possess a shear stresses called the shear stress due to the molecular diffusion. At this juncture, let us understand one more aspect which is very much important to know. The shear stresses which we are applying is basically generating or composed of because of two stresses. Since the molecules are free to move within a fluid from one layer to another layer, in this process, let us say from a molecule moving at upper layer which is moving at a higher velocity is coming to a lower layer which is moving at lower velocity, then since this molecule comes here from a higher velocity layer to a lower velocity layer, then it gets diffused here because it has to slow down. Similarly, when a molecule moving with a smaller velocity moves to a higher velocity layer, then it again due to this molecular diffusion it has to be accelerated. In this process, during this molecular diffusion process, that is a molecule coming from there upper layer to a lower layer and get diffused, and from this molecule here to upper layer. In this process, the molecules carry net momentum exchange, and this generates a stress that is called the shear stress generated due to the molecular diffusion. Moreover, the fluid, that is both liquid and gases, they are also composed of various molecules, and these molecules are basically having the intermolecular forces, and then we have already seen in one of the talks that these molecular forces which are acting within the same fluid are termed as cohesive forces. Cohesive forces. A molecules to move from one layer to another layer, actually the shear stress must overcome this cohesive forces. That means another shear stress is coming due to cohesive forces, in addition the shear stress due to the molecular diffusion. Therefore, a total shear stress is always having two components, the shear stress due to cohesive forces and due to molecular diffusion. If we talk about liquids, then the liquid have the cohesive forces, the shear stress due to cohesive forces is a predominant factor, because molecules are not as free as gases to move, and hence there is a very less net transport of momentum. Whereas in the gases where the molecules are free to move, they have very less cohesive forces. Therefore, the stress generated due to this cohesive forces are very less in comparison to the momentum due to the net momentum exchange. That means, if we see essentially that physically, if we see that if we increase the temperature of a liquid, then since the most of the energy is going and generating the shear stresses, so that the cohesive forces is decreasing because the spacing of the molecules is increasing. In such a case, since the spacing is increasing and the shear stresses is generated due to this increase of spacing is reducing, therefore, the viscosity, which is according to Newton's law of viscosity, stress is equal to mu times the velocity gradient, is decreases. That means, by increasing the temperature of a liquid, the viscosity of liquid decreases. Whereas the gases, when we increase the temperature, the collision frequency among the gas molecules becomes more and more. In that case, in turn what we see, as we increase the temperature, the molecules collide with each other more and more, and hence in turn the net transport of exchange of momentum and in turn the generated shear stress are more. Therefore, the viscosity of gases by increasing the temperature increases. Mathematically, these are represented as, for the liquid, Newton's law of viscosity in two dimensions is given by tau is equal to mu times del u by del y plus del v by del x, where u is the component of velocity in x direction, where v is the component of velocity in y direction. The liquid viscosity somewhat varies as this. You can see that this liquid viscosity ln mu by mu naught a plus b T naught by T plus C T naught by T square, where A, B, C are some empirical constants and mu naught is the reference viscosity at a reference temperature T naught. What we essentially see here, that when we increase the temperature, the viscosity of the liquid decreases. We can also observe that this expression is not having the pressure term. It means that the viscosity of the liquid as well as the fluid is having the effect on this viscosity of liquid due to the pressure is very, very small. Actually, it has been found that both liquids and gases, by increasing the pressure, their viscosity increases. However, this increment in the viscosity due to the pressure is very, very small, and that is why generally it is neglected. Whereas what we essentially talked about, that this mathematically also it is proving that by increasing the temperature, the liquid viscosity is decreasing, because they have the reciprocal to each other, they have reciprocal effect on each other. Whereas if we consider the gas as our consideration, we consider the gas, then it can be said here that mu by mu naught there are two laws, T by T naught to the power exponent n, which is called a power law, and here we can see there is expression called T by T naught 3 by 2 T naught plus S upon T plus S. This is known as Sutherland's law, a very popular law in compressible flow or gas dynamics, where S is called the Sutherland constant and its value is 110 Kelvin, and exponent n is generally from the experimentally obtained value is 0.7. The Sutherland has further refined this formula for particularly for air for the range of pressure from 0.01 atmosphere to 100 atmosphere, whereas the temperature on the order of 0 to 3000 Kelvin. The viscosity of air can be given as mu is equal to 1.46 into 10 to the power minus 6 to the power 3 t to the power 3 by 2 upon t plus 1 plus 1 that is 111. Using this formula, one can calculate the viscosity of air with respect to temperature. Clearly, we can see by increase of temperature, the viscosity of air is increasing. Now, one more fact before we move toward the next transport property. From kinetic theory of gases, it can be shown that the viscosity can be represented as 1 by 2 rho times lambda times V average. It has been seen that when the density decreases, the mean free path increases such that their product essentially remains constant. In turn, the viscosity, when it happens, the viscosity is directly proportional to the average molecular speed of the gas. Since the average molecular speed of the gas we have already seen depends upon temperature, therefore, the viscosity is a direct function of temperature, and hence by increasing the temperature, the gaseous viscosity is increasing, and that's what in whole discussion we have come across. So, you can see that even the kinetic theory of gases also supports the same fact that what we observed macroscopically. Now, moving towards the second transport property is the thermal conduction or thermal conductivity, coefficient of thermal conductivity. Please understand the modes out of the modes of three heat transfer modes, actually, that is conduction, convection and radiation. Conduction is the mode where the actual matter is not displaced while exchanging the heat energy. Rather, the molecules exchanges the similar heat exchange same as the momentum in case of viscosity, and this exchange of heat among the molecules is given by the famous Fourier's law, can be represented as q dot is equal to minus k gradient of T. This q dot is basically the rate of heat transfer per unit area, and k is basically small k here is coefficient of thermal conductivity. And it can be again from the kinetic theory of gases, k can be represented as 5 by 4 rho V average lambda CV, which is all approximately equal to 5 by 2 times mu into CV. That means, the k is also dependent upon the viscosity here and a specific heat at constant volume. Now, the third transport property which we talked about, the coefficient of self diffusion. What happens? Since the gases are composed of a myriad of molecules and they are free to move within the wall or the container which is occupying the gas, and as we start observing the tagged molecule, at any instant it starts picking up a random direction. That means, the molecules does the random walk. If they do the random walk, in this process, if we tag all the molecules, then over a sufficient period of time, what we find, these molecules go and mix each other homogeneously. And in turn, when this happens within a same gas, then it gives a property called coefficient of self diffusion, which describes how efficiently a gas molecules a molecules of within a gas, how diffuses each other thoroughly. And this is given by, in accordance to the kinetic theory of gases, this is given by 1 by 3 lambda V averages. This is also is equal to mu by rho, where mu is called the dynamic viscosity and rho is the density of the gas. In our discussion so far, we have divided the topics as kinetic theory of gases, the basic the review of the kinetic theory of gases, and then we had to discuss the thermodynamics or compressible flow before beginning the actual discussion on compressible flows. So, essentially we have completed the first discussion, the part of the discussion. Now, we move on to thermodynamics or compressible flows actually. Now, whatever we have discussed and derived, let us see, which was microscopic basis. Now, let us see those laws and the derived equations macroscopically, which essentially is discussed in this part of the discussion. Let us have quick review of basic definitions like thermodynamics. Thermodynamics is a science of energy, its forms, its transformation, and its interaction with the matter. It deals various properties of the substances and the changes in these properties due to the energy transformations. Thermodynamics essentially provides no information about the absolute value of energy, rather it only describes the change in energy. Further, we come across the system surrounding and the universe in thermodynamics. What is a system? When we analyze a flow situation where the energy exchange is taking place, a system is defined as it is a particular quantity of the matter or a particular region in space, and anything external to the system is called surroundings. Both system as well as surrounding, they are collectively called as universe. A system is separated from the surrounding by a hypothetical or a real boundary, that is a region that is called or a surface that is called a boundary. When the system has a definite quantity of mass in the investigation, then we call it as a controlled mass. That is, it is also termed as a closed system. A closed system consists of a constant amount of mass and no mass is allowed to cross the boundary, system boundary. Now, however, the energy from this system can definitely cross, that is, it can come in or go out. For example, this is the image which I have inserted here, the bomb calorimeter. What you can see here, when the solid lump is put, which is a heated one, and this is the, let us say, a liquid inside, when the heat is transferred from this lump fluid, the solid lump or solid body to the liquid, what is happening? There is a temperature change which is measured through thermometer. What essentially is happening? This solid body is called, let us say, a system, and now since it is transferring heat to the liquid, this becomes its surrounding, and the effect are seen that the temperature of the surrounding is measured in terms of delta T. However, the whole system is insulated and then it has a adiabatic walls, that means from this complete system as well as its surrounding, no heat transfer is taking place, and then this system and that surrounding, this system plus surrounding becomes a universe. Now, moving on, the energy. Energy is the capacity by which a system is able to deliver the work. The various forms of energy, microscopic energy, the macroscopic energy is something like, for example, kinetic energy, potential energy, electrical energy, the energy due to gravity, or surface tension, etc. Where is the microscopic form of energy which we have reviewed in the kinetic theory of gases, where translational energy, rotational energy, vibrational energy, moreover electronic energy, when the bonds are formed, this is called the bond energy, and then in the nucleus, that is in the chemical energy, where the bonds are broken in the reactants and the products are formed. Moreover, since within the atom the nucleus has the both neutrons and proton, and when it is releases, we call it a nuclear energy, which is utilized in both the nuclear and hydrogen bomb. Now, properties of a system. The property of a system can be categorized in both intensive and extensive properties. Intensive properties are those properties which are independent of mass, such as pressure, temperature, density, and specific properties. Extensive properties are those properties which are dependent upon mass. Note that when you divide when you convert extensive properties to intensive, that means that itself becomes a specific property. That means, suppose the volume which is dependent upon the mass, if you take the volume per unit mass, then it automatically becomes an intensive property. And we have seen that the specific volume relationship, that PV is equal to nRT in our discussion in the derivation from the kinetic theory of gases. Now, further, what is a thermodynamic equilibrium? In thermodynamics, we always talk about thermodynamic equilibrium. Thermodynamic equilibrium essentially says that a system must be, whether it is a gas or a region in space, must be thermal, mechanical as well as chemical equilibrium. In addition to this, there should be phase equilibrium. The thermal equilibrium says that within the system there should not be any temperature difference present. The mechanical equilibrium says that at any instant of time under observation of this system or region in space, the pressure must have a definite value, and it is not changing with respect to time. Phase equilibrium, that when the system involves two or more phases, then in the equilibrium, to be in the phase equilibrium, the mass of each phases should stay in the equilibrium mode. Chemical equilibrium says that there is no net chemical reaction should occur within the system, and when the complete system is in thermodynamic equilibrium, then it has to be in thermal, mechanical, phase as well as chemical equilibrium. Now, we will see what is processes and cycle. This is a PV diagram where a process shown from, let us say, a system is taken due to some change in property, heat addition, work transfer, from 1 to 2. Now, since the path is followed as, let us say, designated as path A, and from 2 another path is taking the system back to path is at the state 1 using the path B. These paths are basically a series of the states of the system through which the system is changing its state, and the process from one state of the system to another state is that is the property of a system is changed, that is called a process. Now, when the system is taken from a state 1 and using the path A becomes and reaches to state 2, whereas in the reverse process it has taken path B and then again back to the original state, then this complete cycle, this whole path A and path B makes this as a complete cycle. Now, the process which we said it here, that system from one equilibrium state to another thermodynamic equilibrium state reaches, this can be taken through various processes. That means, they are categorized as, if the process from state 1 of the thermodynamic equilibrium to state 2 is taken such that the temperature of the system is constant. Then this kind of process is termed as isothermal processes. Whereas, if the pressure remains constant while taking the system from 1 to 2, it is called isobaric processes. However, when the volume of the system remains constant while taking it from system 1 state 1 to state 2, it is termed as isochoric processes. Now, please see here that the pressure versus volume diagram, it is designated. This is the process in whichever order it is taking place. These upper lines, this and this, are isotherm. Isotherms means it is showing isothermal process, constant temperature processes, whereas these two lines are termed as adiabatic processes. Whereas these lines in this second paragraph, the graph, what we see, the upper line, this and this are isothermals, whereas you can see these vertical lines which is designating as isochoric or constant volume processes. Again here this the pressure is constant here, what we see here, this is called isobaric processes, whereas this curve is adiabatic processes. What is an adiabatic processes? The process in which the heat, there is no heat transfer is taking place from the system, that is the system boundary is insulated, we call it as adiabatic processes. Moreover, we also say that the process, all these processes are reversible. If reversible, that means when the system from state thermodynamic equilibrium of state 1, it is reaching to state 2, then if by path B it reaches again to state 1 such that any trace on this system as well as surroundings can be reset, that is no trace on the surrounding by this system in undergoing these processes is left, then we say the process is reversible. That is, everything, whatever the effect was carried out from taking the system from 1 to 2 is reversed back. When the process is adiabatic and as well as reversible, we call it as isentropic processes. Further, let us see the first law of thermodynamics. The first law of thermodynamics essentially is the conservation of energy, which says the energy can never be created or not destroyed. Only one form of energy is converted into the other form. That is the basis of first law of thermodynamics. It stipulates, that is, on no it stipulates no restriction on the direction of the process, as long as the energy from one form and other forms are balanced, that is happening, it does not stipulate any direction of the energy transfer. To satisfy, that means which direction the process should take place, the additional law, that is none other than second law of thermodynamics, is brought into the picture. So, therefore, let us see the first law in more detail. For a closed system where the system boundary is such that no mass is crossing across the system boundary, where the energy transfer can take place, this is called a closed system or a fixed mass. If del Q is a small amount of heat is added to the system, and therefore, del W denotes the work done by the system on the surroundings and vice versa. Sign convention says that when the heat is supplied to the system is positive, whereas the work done by the system is positive. Under such condition, writing the first law of thermodynamics, before that we can see also here that one more point, that we have designated del Q and del W. These represent the inexact differentials. That means, both del Q and del W are inexact differentials. What does it mean? The inexact differentials means the change in heat transfer as well as the work carried is a process dependent variables. That means, they are not state variables, their change is dependent upon the process through which it is carried out, and that is why they are represented with del. Moreover, in this exchange there is another property which in kinetic theory of gases we defined as internal energy, that is the energy of a system. We said that is when the center of mass of the molecule of the gas is at rest. That means, the first law says that whatever the energy is supplied, it first the firm portion of this is goes to change in its internal energy, and the remaining portion goes towards the delivering the work by the system on its surrounding. This internal energy in turn a state variable, that is why it is denoted by whole du. Writing the first law of thermodynamics in mathematical form, we can state that del q minus del w is equal to du. Here du is nothing but what we have used is dE in our gas kinetics, this du. Now, there could be infinite number of ways to occur which satisfy this relationship, that is from taking one thermodynamic equilibrium state to another thermodynamic equilibrium state, there could be infinite number of ways to reaching from 1 to 2. However, in compressible flows, that is gas dynamics, we are interested in 3 processes only. First is adiabatic processes, that is the system boundary is insulated and it is not allowing any heat transfer. Second thing is that the process is reversible, that is the whatever the effect by taking the system or changing from one state to another state can be totally reversed without leaving any traces on the surroundings, then we call it as a reversible process, and both reversible and adiabatic processes are called isentropic processes. So, these 3 processes we deal in compressible flows, which we will come across. Now, moreover, in open system, where in contrast to the closed system where the system boundary across which the mass transfer was not happening, in open system the mass transfer is taking place, and this is because of this the open systems are able to deliver the work, useful work, because the mass in the open system is continuously being replaced, and therefore, in addition to the internal energy, here another function, a heat function or also called enthalpy is defined, which is termed as U plus PV. P is the pressure, V is the volume, and this PV is also termed as flow work. Hence, the total enthalpy H is defined as internal energy plus flow work, and this property instead of internal energy is used in the open system analysis. Now, since the open system the mass transfer is taking place, that is the original mass is being shifted, replaced by new mass, and that is why the open system are able to do work, useful work. Now, let us see this diagram. Here this is the system where some fluid is there which is moving, and to analyze the situation we have hypothetically assume that there is a hypothetical piston is here in this cross section, which is having where the fluid is entering at the velocity v1, and let us say these are 2 heights from the datum z1 and z2, that is the mid plane, and this fluid which is entering in here is coming out at the section 2, where the velocity of the fluid coming out is v2, and suppose in doing this process, if the fluid which is this said by is shown by this dark fluid is moved by a distance d1, then after doing this, going from all across the layers, this same fluid is coming out with travelling a distance d2, a small distance. Under these circumstances, since the mass is being replaced continuously in the open system, a shaft work is carried out, that is a useful work is carried out by the system, and let us say Q is the heat supplied to the system. Now, under this condition, the total energy can be defined at any section 1 or section 2 as internal energy, kinetic energy and the potential energy. Because the datum is having, the mid plane is having from a datum z1 height and z2 height, hence we can say the total energy at the section 1 is E1 U1 plus half mv1 square plus mg z1. Now, similarly, E2 can be written as U2 plus half mv2 square plus mg z2. Now, further moving ahead, what we see for an open system, we can write down the first law of thermodynamics as Q12 minus W12 is equal to the change in internal energy. Now, substituting back, Q12 minus W12 can be written as U2 plus half mv2 square plus half mg z2 minus the at the section 1 the total energy, that is U1 plus half mv1 square mg z1. Therefore, as we assumed here, let us say a fluid mass by a hypothetical piston, if it is moving a small distance delta 1 or d1, then we can say with the definition of the work, we can find out that the force applied, let us say if it is F1 and moving this delta can be written as d1, and here again d1, then we can say that force F1 which is applied at the section 1, we can say minus P1 A1, where A1 is the cross sectional area at this zone. That means, here this is A1 and here it is A2. Now, a imaginary force is pushing the fluid lump here, fluid mass here inside, which is here fluid mass is coming out here at section 2. In this situation, what we see here, that since the fluid is pushing inside, therefore, there is a minus sign because the surrounding is doing the work at the system. Therefore, minus P1 A1 is equal to into d1, that becomes A1 into d1 becomes the volume of the fluid mass minus P1 and V1. Now, note that this negative sign is also because the property of the work, definition of the work is, since this is being a scalar quantity, is defined as the dot product of force and into distance. At section 1, since the distance travelled here is in both force and distance travel are basically in the opposite direction. Under this condition, the cos product, the cos in between these two vectors will be 180 degree, and since cos pi is equal to minus 1, and then the W1 becomes negative here. And since this is again the flow work at section 1, similarly doing this exercise at section 2, we obtain W2 as P2 V2. Substituting back, the W12, that is the total work done by supplying the heat Q12, can be termed as Ws, that is useful work, plus P2 V2 positive at section 2 and minus P1 V1 at section 1. Now, substituting back this quantity into the original gas first law of thermodynamics, what we obtain Q12 minus Ws is equal to U2 plus P2 V2 plus half mv2 square plus mgz2 and minus of with the same quantities with subscript 1. Now, clubbing this U internal energy and flow work, we can write down this as H2 and this quantity as H1. Hence, rewriting the equation further, what we find that H1 plus 1 by 2 mv1 square plus mgz1 becomes right hand side H2 plus half mv2 square plus mgz2 plus ws minus q12. Now, in gas dynamics applications, since it is a high speed flow, therefore, in comparison to the kinetic energy, the potential energy or change in potential energy is very, very small, therefore, neglected. Further, since the process, if the process is adiabatic, then q12 can be termed as 0. Moreover, the flow process around an airplane, which is our matter of interest, that because a flying object is airplane in the sensible atmosphere, therefore, any shaft work is also 0. Under this, the equation this reduces to the following form, that is H1 plus 1 by 2 mv1 square is equal to H2 plus 1 by 2 mv2 square. That means, H plus 1 by 2 mv square, which can be designated as a new variable H naught, is essentially constant, and this H naught is termed as stagnation enthalpy and H is termed as static enthalpy. And hence, if we divide by m, we can bring out the relationship H naught is equal to H plus v square by 2, where v is the velocity, H is the static enthalpy, H naught is the stagnation enthalpy. This is the most useful form of the equation in the gas dynamics. Now, let us give a pause here, because we have introduced two new terms distinguishing each from each other, that is a static enthalpy term and a stagnation enthalpy term. Please note that whenever a flow is taking place and if this flow is brought isentropically to the rest, that is reversibly and adiabatically, then whatever the thermodynamic properties will be present at that state, all are, that is the flow at rest which is brought isentropically is termed as stagnation properties. That is, if the properties of a fluid flowing fluid is pressure P, temperature T, density rho, then it becomes stagnation properties P naught, T naught and rho naught, where the naught, that is P naught stagnation property, P naught, T naught and rho naught, they define it that this is the property evaluated when the flow is isentropically brought to rest. And all these properties are always more than your static properties. Since this we have said this is the most useful governing equation of energy in compressible flows, we will keep using this equation for deriving additional equation. Now, let us see the condition of applicability for this H naught is equal to H plus V square by 2 in specific terms, that is per unit mass. Now, since this is applicable when the flow is steady, the gas should be an ideal gas and there is no external work, that is no useful work was carried out, and the process should be adiabatic. Under this condition only this equation can be applied. Now, moving further, since we said that the first law of thermodynamics stipulates no preferred direction or does not restrict the direction of the process, and the process is carried out under as long as the energy is conserved. However, in reality it never happens. For example, here we have taken, let us say there is a hot body and there is a cold body. From our childhood days, even we have noticed that always a hot body gives the heat to a cold body, and then the cold body temperature increases where a hot body temperature goes down. But if we see reverse then if we apply the first law of thermodynamics, it says yes, it is possible, because whatever the energy transfer from here is taking place, it is going to the cold body. However, if we reverse the direction, that is, if suppose the cold body starts giving the heat without any external interference to the hot body, then also since the energy is conserved, the first law is valid. However, our intuition says that this never happens, that without any external interference, the cold body never gives the heat to the hot body. This process is checked, that is, the checks are applied through the second law of thermodynamics, which stipulates the correct direction of the process, such as here. For this purpose, there is another quantity defined as S, that is called entropy, or the amount of disorder in a system of the system. Suppose if T is the temperature of the system, if this T is the temperature of the system. Now, if T is the system temperature and del Q is the heat transfer in a reversible process, then D, that is in reversible process, the heat is supplied to the system, then it can be written as ds is equal to del Q times del Q reversible divided by T. And since entropy is a state variable, it is represented as ds, that is, again it is an exact differential. Therefore, being a state variable, the entropy, that is change in entropy, is always have the same value ds, does not matter whether the system is brought through a reversible process or an irreversible process. Therefore, let us see that suppose if a system is brought from state 1 to state 2 through a process A, which is reversible. However, there is another process which is process B, which is irreversible. Then in the second case, unlike the previous case where ds was exactly del Q reversible by T, now here we write ds is equal to del Q by T, where this quantity represent that the heat transfer to the system under irreversible process conditions. Then an additional term ds irreversibility comes into the picture. Since ds irreversibility is always greater than 0, that means there will always be some losses, that is amount of disorder will always be increasing into the system. Therefore, both by seeing the second equation this as well as the first equation this, we can write this equality as inequality form, that means ds of total universe system plus surrounding is always greater than del Q by T. It means if the process is further, we say that if the process is adiabatic, we say ds universe is always greater than or equal to 0, where equality holds for reversible case, where and inequality holds for irreversible case. That means a process will always go in that direction where the entropy of the whole universe increases. However, there is a caution. We should understand that suppose this law holds only for total system plus surrounding, that is called universe. However, if we are particularly investigating a system and if the heat is extracted, it may happen that the entropy of the system becomes negative. In some or other examples, we can definitely come across this situation. Now, here we see here the system and the surrounding, that is totally called as a total called universe, which we are coming across. Now, if this ds, we said the process is called irreversible process, and when ds is equal to 0, then we call reversible process, and the isentropic process are when the both adiabatic and reversibility are valid, and hence in these cases the entropy remains constant. Now, here we have just said it that in a non adiabatic process, when the heat is sometimes extracted from the system, the entropy can become negative. Now, let us see one very important concept, a thermally perfect gas. What is a thermally perfect gas? Please understand that any gas which obeys the thermal equation of state, in our case let us say ideal gas, if it obeys the equation of state, that is the ideal gas law, written as P equal to rho R T, or more precisely PV is equal to RT, because rho is nothing but reciprocal of specific volume. If the gas obeys the ideal gas law, it is called thermally perfect gas. Therefore, the thermal properties are pressure, temperature and density. Moreover, if the gas has the calorical properties, that is internal energy, enthalpy and entropy, any relationship between the internal energy U, H and S, that is calorical properties and thermal properties, those equations are called calorical equations of state. A gas has becomes thermally perfect when it is both thermally as well as calorically perfect. Now, moving further, let us see that internal energy can be written as a function of, to fix the state of a system, internal energy T and V. We can write down the differentials such as du is equal to del u by del t dt plus del u by del v into dv at constant t. Now, if the volume is kept constant, that is under isochoric process, this fellow goes to 0, and hence we are left with du is equal to del u by del t at constant v dt. Note that we have in the kinetic theory of gases, we have already said that this term is nothing but your Cv, that is specific heat at constant volume. Therefore, the du can be written as Cv dt. Now, similarly, if this exercise to fix the state using two properties of the system, thermodynamic property H is equal to Ht and P, then we can say here that dH by del T, again writing the partial differential form at constant P dt, del H by del P at constant T dP. If the process is isobaric, again this term goes to 0, and then we are leading with dH is equal to del H by del T P dt, and from the kinetic theory of gases we have seen this is nothing but Cp, writing this in this form dH is equal to Cp dt.